Chris Rackauckas, a research affiliate and co-PI of Julia Lab at the Massachusetts Institute of Technology, Director of Modeling and Simulation at Julia Computing, and creator, lead developer of Julia Sim, Director of Scientific Research at Puma's AI, and creator, lead developer of Puma's lead developer of SciML open source software organization. I welcome Chris Rackauckas.
Yeah, thank you very much. Thank you. Thank you for the kind introduction. I think everyone's going to be streaming in here, coming in from breakfast, and as everyone's coming in, everyone will have this thing on their mind where everyone's working today, but also at the same time you're thinking, am I working tomorrow? Because AI is kind of coming for me, right? Okay, it's kind of a joke, but actually it is the question that everyone's asking at the breakfast table, right? So I thought what would be pertinent is to update what I've been talking about before. The last few times at JuliaEO, I was talking, here's scientific machine learning. Here's how you do things with AI and machine learning, right? And here's how you make it a little bit better, right? But this talk is really now kind of the evolution of that, to basically just say, here's everything that's going on. Here's how you use it. But here's how you become a more effective scientist. So that way, as these things are obsoleting the old way of doing things, this is how you stay relevant, right? And I want to kind of bring this from the point of not just, how do you write a few things in a computer, what do the scripts look like, what's the Julia code look like, but I want to show you the problems going on, how things are evolving, and what that means for how you should be changing how you do computing, right? So let's start. So let's start with talking about the bitter lesson of AI, right? Because the bitter lesson of AI is kind of the core of where everyone talks about, where machine learning is going. This is something that's attributed to Rich Sutton from 2019, and he talks about this idea that general methods which leverage scalable compute will outcompete everything, right? The idea is actually pretty simple, right? So let's say you have a method that is 10 times less efficient, 10 times less efficient than your very, very detailed thing. So you have one solver that is able to solve all equations, and it's 10 times worse than the type of method that is specific to your one equation. But if you just build a big enough computer, you're good enough. So as long as you make as long as that method that is 10 times worse, as long as it's parallel, and as long as you can get a nuclear power plant, as long as you can be NVIDIA and get $1 trillion of GPUs, then you can outcompete the person who is then trying to make a very specific method for a very specific problem, right? Again, I'm not going to say that I'm 100% in this idea, but this is the idea that was put forward, and this is the idea that's driving the AI revolution, right? It's not like, there are some people that are going to tell you that what's driving it is the idea of AGI and, Terminator is going to come for us. No. Like the true idea and computer science behind it is this idea of the bitter lesson of AI, which is that if you work on scalable general methods and then you work on making it so that way they just scale for lots of compute, this is a tool and a method that can outcompete in many scenarios, right? And so where Richard Sutton really talked about this is the idea of, if you look at what happened with chess, right? It took decades and it took a lot of researchers who knew a lot about chess to be able to beat Deep Blue. And it was just barely able to beat a grandmaster, right? But what happened next was general methods. So a method that was just say, okay, it's not really a bot that is for learning how to play chess anymore. Let's build a reinforcement learning agent that learns how to play games. And let's let it play 1 trillion of these games on tons and tons of compute. And this is what you get with the version that started being the alpha, all the things that you start with going with AlphaGo, and suddenly you start being able to say, oh, chess is an easy game. What about Go? What about StarCraft? And basically you start to have a method that scales to all these different methods. Now, it takes $1 billion of compute for this technique to work here, but it was something that suddenly was able to unlock the code to say humans are no longer the thing that that will win at almost any game. And it was not by creating a bot that is better at Go, not by creating a bot that is better at StarCraft. It's creating one method, a reinforcement learning method that is built on scalable compute and just scaling that compute to astronomical levels, right? And so this is also where speech recognition and all this stuff with natural language processing came along. wrong, right? Instead of saying, hey, look, let's build a database so that way we understand the word in English, we understand the word in Spanish, and now we have translations between them. Oh, now we have to repeat that work when we go to Portuguese, right? That's not how all these machines started to work, right? You had one thing where you said, okay, let's build an engine that is able to take a corpus and text from one, and is able to take a corpus and text from another, and is able to learn the translation between these using translated pages like Wikipedia and these sources, right? And now let's just take this and just make sure that we put into it trillions, of gigabytes of data and trillions of compute, billions of dollars in compute. And if we do this scalable compute way, sooner or later, it will outcompete the experts building a translation engine, right? So this is the bitter lesson of AI, that what has been learned through decades of AI research is that these general scalable methods outcompete experts trying to build expert machines. And this seems to be quite the path where a lot of things are going, right? And so, again, I'm not saying that this is where everything is going, but this is really the core thesis behind the AI revolution, that sticking to methods that are scalable and general ends up outcompeting the things that are specific to domains. And so one thing that we need to then kind of understand then is, okay, that should be scary to hear as most people who are scientists, because what you do is you build specific methods for specific problems, and so you must go, am I going to is there going to be a general neural network that will start to build a climate model better than me, right? And so I think that that's not really the right way to think about the problem for where humans will be in the near future. I think what you need to start to think about is, where do these methods have issues, and how can humans be the ones to cover those gaps, right? And so let's start to investigate a little bit of this. So one potential problem that happens in all these different systems is out of sample data, right? So basically when you train all these systems, right, they don't actually know anything, for example, about language. When you're training a system that is doing translation, it just knows all the language that's there on the internet, right? And it's going to learn sooner or later everything that's written on the internet, how to translate from language 1 to language 2. But what's something that's out of sample is, for example, all the stuff that comes up with slang, right? So, if, for example, in Tessera, there's all this random slang about, for example, getting hit by the fifth bull, right? So there's 4 bulls that come out in every bullfight, and the 5th bull is, when you get hit by the hangover, right? So, this is something where if you try to put this into Google Translate, it will never learn this because there's none of that corpus in there, right? And so there's still a place for humans to go, which is understanding where the data doesn't work, right? And so I think that this is a great example because here's an example of a Tesla. Where there's a full moon out there, but the Tesla was never trained to be with such a large full moon, and so therefore it believes that the moon is actually another car, and it slowed that in the car and almost caused a car accident because it saw this gigantic moon, right? So this is where you can start to see that, yes, a complete learning system, if you give it infinite amount of data, it will be able to do everything. But in the real world where you don't have infinite amount of data, there are certain things to be able to program into the system, like the moon is not part of the Earth, right? That even though that is a light, we know through certain information, things like parallax, that light signal is actually so far away that you shouldn't be considering it as actually in front of you, right? And this is some kind of information that we somehow need to be building into our systems. Another really great one is, so here you can see there's all these traffic lights that are hitting the car, right? And we'll see in a second that it's actually just driving behind a truck that has traffic lights in it, right? And so again, this is not a scenario that was part of the training of the self-driving car. And so the self-driving car engine has no idea what to do when it's driving behind a truck with traffic lights, right? And so these learning systems, they technically work in the ideal world if you have infinite information and if you've seen every single possibility. But this shows you that there's always possibilities that you don't run into. And what humans can start to do is start to cover these gaps for which, because we can extrapolate out and understand that is a truck with traffic lights in there, but a system that does not truly understand what's going on in the world will not be able to make that extrapolation, right? And so this is one piece that we can start to think about, right? That what humans have been able to do, that AI and machine learning is not good at all. Even after $5 trillion of putting work into this, even after all this, ML and AI does not generalize beyond the data sets that it's been working on, right? So how is Sam Altman trying to deal with this? How is Google, Satya Nadella trying to deal with this? They're just trying to find more and more data to be able to cover literally everything that's going on. But if you don't believe that you can literally get data for literally everything, then this tells you one thing that a human can do, which is to help make sure that what the behaviors are of these systems when they're going beyond their data set, when they're trying to extrapolate beyond, right? Trying to make sure that we can control, constrain, and understand what's going on beyond the training data set. Now, here's another thing to take a look at, right? AI and machine learning really started to take off in areas such as I was playing computer games or in video games. Now, why is this the area where they started to do a lot of their work early on and show a lot of their demonstrations? The reason is because it is exactly this kind of scenario where you can get infinite data and the data is perfect, right? So all these groups like DeepMind and DeepMind was a really big one, right? They got billions and billions of dollars, and they said, how are you going to show me that AI and machine learning is going to work? Well, they said, we're going to make it play Mario first. We're going to make it play Go first. Why did they do that? Well, because inside of the game of Mario, you know exactly all the parameters. You don't have this real world thing of like a truck with traffic light that comes in. There's one game, and you can play the game infinitely number of times, and so you can get as big of a data set as you want. And so basically the AI and machine learning companies, right, really started to say, we were going to show everyone that the whole world is going to change once we get enough data by using this as our playground, right? OpenAI and DeepMind did this. And they did it, right? They showed that with infinite data, they were able to beat every human at Go, beat every human at StarCraft, beat every human at pretty much every game they threw it on, and they said, this shows us what the future is going to be. But I think actually it was a double-edged sword, because it showed us that it could be the future, but it showed us an alternative issue as well. Right? One of the things is that it demonstrated overfitting issues, and there's a lot of interesting overfitting issues that it was in particular the humanoid robot groups have found, right? So here's one example. So a coworker is teaching an agent to navigate the room. The episode terminates as the agent walks out of bounds. He didn't add any penalty if the episode terminates this way. The final policy learned to be suicidal, because basically it's a robot that's trying to get to the right place, but if it does the wrong things along the way, then it loses points. But if it leaves the game area, then it suddenly just terminates the game. So what the agent learned how to do is it said, okay, if I kill myself instantly, then I will never have negative points. And so, boom, there you go. And so it basically, and so we started to learn that, if you let these learning systems try to build their own policies, they can start to find these very adversarial effects, which you really don't want to happen. And so, this really became an issue when you started to look at a lot of things going on with self-driving cars and self-driving airplanes, because these policies of, what if I just drive over one squirrel, I guess that's better than a baby, these things actually started to be, found and actually a part of what is driving cars. And this is the issue that is starting to become, that was becoming present in our society, right? So, there's this overfitting issue that became even apparent even when it was just doing things like playing little video games, because it could find adversarial kind of solutions. But the other thing that started to come up as well was we started to learn what the real cost of all these things were. So I'm just, there's some open data. Now, some of these numbers are a bit approximate because not all of these numbers are open, but there's a lot of speculation as these numbers. So I put one source there that has some of these perspective numbers, but there's also some hand wavy around like, oh, so-and-so estimated this using the power output of this power plant, yada, yada, yada. So take these numbers for a little bit of a grain of salt, right? But you can see that as the complexity of the system grew, there's an exponential cost growth, right? So for example, in order to train a bot in order to play Go, it costs $35 million, which, okay, if you're a PhD student, that's a lot of money. If you're Google, Google's like, that's a little bit of money for a bit of PR, right? GPT-3, so the natural language processing system that we said was not good enough to truly use in practice, that was $10 million, right? When you start to get to Alpha Star, it was about $12 million of research for the final run, but about $1 billion to be able to do all the training that was going on in the game in the first place, right? So about $1 billion to make it play a game of StarCraft, where then in the last game, one of the pro players found out how to make it do the wrong thing. So that's a good use of $1 billion. And GPT-5, the actual training cost was about $500 million. But that's actually just them clicking the button and the power to run the compute of the system. The estimated cost for GPT-5 was in the tens of billions of dollars, right? So you can see the evolution of this, right? You have, the GPT-3 era was about 10 million, and then you had an era of about 100 million to 1 billion, and now we're in the era of tens of billions, right? And so when people are starting to say, GPT-6, ChatGPT version 6 is going to come, and it's going to be, a little bit better, right? Remember, the difference between ChatGPT version 4 and version 5, it's a slight improvement, right? The next one is going to also be a slight improvement, but looking at the way that this is growing, it went from $1 billion to train version 4 to tens of billions for version 5. We're looking at hundreds of billions for version 6, right? And this tells us that, even though we might be scared about how these things are evolving, really, if they have to 10x the amount of in order to be able to evolve each time for this little tiny improvement, how many more 10x's in dollars is there really going to be left, right? We really should be questioning how much better they will get from the state that they are right now, because they're really starting to hit a limit here. And so, this is just some more quotes about this. So, for example, one of the things that's happening right now in the United States is that Pennsylvania's dormant 3 Mile Island is actually, it's an old nuclear power plant, was actually bought by Microsoft to be able to be turned back on, because they need to have a new power source for their new data center for the new training, right? So we're talking about we need, the next training is probably going to take on the order of hundreds of billions of dollars. Literally, these companies are requiring to buy and build new nuclear power plants in order to make this happen, right? So this is not just perspective willy-nilly, it might cost that. They're literally already putting the hundreds of billions of dollars in to build out the infrastructure here, right? So they said, again, Sam Altman said that the GPT-4 was in the 100 million range. They said the 2025 model was in the $10 billion range. So that was GPT-5, right? And then so GPT-6, they're saying that they're going to 10x this again, 10x this again. And so we're really looking at something where we're talking about, the Stargate project, which is the next one that's coming from OpenAI, the one that's being built down in Argentina. They're talking about their next one being a $500 billion training project, right? So while what I will show you a bit later and how all this automated coding techniques actually work, and again, you should start to be using them today, there is something that you should be thinking about in the back of your mind, being how much more will they actually scale, because this is how the costs are truly scaling, right? So, if you think that they're going to get perfect, I will question whether you think, whether there's going to be the next doubling going on in this space. So what this really kind of talks about then, what I'm really trying to hit on then is that, we've been building on this idea of the bitter lesson of AI. And the thing behind it is, what we have learned is that over time, if you just have a general method where you only try to work on a general method that scales with compute, this outcompetes everything in the long run, right? And this kind of worked for the first 6 decades of AI research. But we're starting to hit a point in the scaling where you say, okay, in order for us to scale more, we're going to need to, build new nuclear power plants. We're going to have to create nuclear fusion. We're going to have to build a Dyson sphere around the sun. We're hitting a level of scaling where it just does not even make sense for the amount of energy that the human race creates, right? So it's no longer something where you just say, hey, let me build a bigger computer. Now it's, hey, let me try to get all of the power of the entire country of Denmark, and then that's the only way I can train the next version of my system. But my scalable general system will be better if you give me all this power, right? We're starting to hit the edge of where the bitter lesson of AI actually starts to work. So if this is the case, then where do humans play, or what is the next thing that's going to be going on in this space, right? So with ML and AI scaling costs growing exponentially, is there a right way around these issues, right? This is the thing that we should start to ask. Is there a way for us to be able to maybe change the thesis a little bit, or change the way we work with these systems such that we can still get the next doubling, the next order of magnitude increase in productivity, with the fact that we know that these techniques are kind of leveling off in how good they're getting, or they will at least take, another 100 billion, 1 trillion to get the next tiny improvement, right? And this is where we start to look at these new methods, right? So, again, this is a hand wavy kind of plot here, right? But this is where the talk is really focusing on, this purple line, which is these methods for scientific machine learning and agentic AI, right? what these methods are really starting to look at is, given that we have these scalable general methods, right? Given that we have methods for training neural networks, given that we have methods for agentic AI, what are the techniques in scientific computing and in the way that we do mathematical modeling that incorporates these as a central element to be able to accelerate how we do science, but does not rely on them to solve the entire problem, right? And this is where we're starting to look at, okay, if you use these methods, so let's say if you use everything machine learning has to give you, you're going to at least do as good as machine learning. But maybe we can do a bit better because maybe we can fill in those gaps that the AI and machine learning techniques could not do in the world of finite data, finite money, finite power, right? And so there's really kind of two solutions then kind of going forward that we're really looking at. One is the space of scientific machine learning. The other is agentic AI. And so how do we kind of think about what these two things are? The piece of scientific machine learning is adding scientific models or adding scientific knowledge to scalable AI model methods, right? And we'll go into very deep depth about this. But the key idea behind this is, instead of trying to get the machine learning to learn everything, what we can do is that we can use our expert knowledge and our ideas of science, and we can augment it with scalable machine learning systems to do better than just a scalable machine learning system on its own, right? So this is one path forward that is really kind of saying, I accept everything that's going on in AI machine learning, but I'm going to now try to beat it by having me involved as well. Right? The complete other way is this agentic AI, which is to say, hey, look, there are all these systems like ChatGPT, large language models that are trying to automate the coding approach, but how can I, as a scientist who does actually know something about my domain, how do I use these tools and how do I use this to be able to be a better scientist, right? And so the first part of the talk is going to be all about scientific machine learning, which again, I've given a version of this talk a few times before, so I'll do this one a little bit faster. But in the second part of this talk, I'm going to go into the agentic AI systems, the bot armies we've been building out for running the SIMO organization, and how we've effectively placed, a few undergrads or so with an army of 50 automated bots continuously running. And I'll show you exactly how we get this all set up, so that way everyone who's leaving the room today can also have their own bot army running. But again, that's the second part of the talk. First part of the talk will be scientific machine learning. Right. So what's the motivation behind scientific machine learning? So the motivation behind the scientific machine learning approach is twofold. One is to say that, let me make sure I keep track of time just so that way I can do all this beautifully. All right, about halfway through, exactly might be where I want to be. So the idea behind scientific machine learning is that when we do all these AI machine learning methods, we say, if I have enough data, then I'll be able to make good predictions, right? So you say, oh, if I have, here is showing some biological data, but we want to be able to say, okay, if we have biological data, if we have chemical data, we have data of everything that's going on in the atmosphere, in the clouds, if I have enough of this data, then the machine learning should be able to learn from it and make good enough predictions, right? But the key insight to have is that has a very strict reliance on homogeneous data, right? Like when we say machine learning is working on data, we implicitly mean that it's on homogeneous data. What do I mean by that? Well, everyone here that's been training neural networks, right? You know that your neural network has to have the same kind of input, right? There's a number that you have to have some kind of input where you say, okay, it has to have 128 different values. All those values have to be floating point numbers. Like there's a homogeneous input that has to go into your neural networks. And it turns out that is not all the data that we have in science, right? I think a very good example of non-homogeneous data that is captured in scientific knowledge is how do we know about general relativity, right? So everyone here probably knows what general relativity is, even if you don't work in that area of physics, right? And everyone here probably knows at least something from watching Cosmos or some Netflix documentary about how we know how general relativity is true, right? Now the thing is, there is no machine learning level data set that could train an AI general relativity. Because the way that we know about general relativity is true is actually a few different facts, right? One of them is Thomas Eddington's experiment, where when there's a solar eclipse, you can actually see the stars move, right? There's gravitational lensing. We've seen gravitational lensing in other cases as well. One other major prediction is the perihedron of Mercury, right, which is one example that I'll be able to show you in simulations. Right, the orbit of Mercury is not circular; it ends up being a Lissajy pattern, and that's one direct prediction of general relativity. Another reason why we know this is if you try to run the GPS satellites, right, you have to take into account time dilation. So I know a lot of people here that work on with satellite data actually have to take into account relativistic corrections, right? And from all these pieces of data, we know those equations of general relativity must be true. But there is no single trillion gigabyte data set that tells us everything about general relativity is true, that follows one format that we can put into a neural network that has the same number of inputs, that has the same, that isn't what's generally true about science, right? We have heterogeneous data. We have different experiments that all combine to give us one scientific theory. And that is exactly the kind of thing that machine learning cannot deal with, right? Neural networks need homogeneous data to train on, which is not what we have in scientific experiments. And so what we can start to do is we can start to say, we have scientific models, right? So here's, for example, a scientific model, say a biological system or some chemical system, where someone did one experiment to be able to say, hey, look, I know that this chemical and this chemical interact with each other because I put it in a vat, right? And I actually showed that these chemicals work together. And someone else did a molecular dynamics experiment and showed, hey, look, these two chemicals bind to each other. So I know that this arrow is true. And then someone else did another experiment and showed that this arrow. And after building out a scientific literature over 20 decades, we're able to say, hey, look, this is how this area of the biological organism, this is how the chemical reactions work, right? There's no single data set that we can point to, then train an AI agent or some machine learning to be able to incorporate this. But this is scientific knowledge that we've gathered, right? And now while I talk about this in the area of biological systems, this happens all the time in other systems as well, right? And this is how we know about cloud dynamics, right? We don't have, for the dynamics of clouds, for the dynamics of plankton in our climate models, right? We don't have a single data set where we just say, hey, look, this data set has been tracking everything for so long, and this tells us everything about how plankton works, right? You do have that data set. It tells you a little bit about plankton, but then someone else actually takes plankton out of the ocean, plays with it, and writes a piece of paper that says, oh, hey, look, here's a chemical interaction that you could take into account. You have all these hundreds of papers, and then the climate model has a human that takes all of these different experiments and puts them into a scientific model, and that model is what gets incorporated into your climate models, right? And so now what we need to think about is, how do we pair these two approaches, right? How do we pair the approach that says, I can learn everything from data, and this is something that we need to take into account, it's the future because it really works well, but there are certain things that we cannot get those levels of data sets. We will not get that size of data set, but a human will be able to synthesize it from homogeneous data sources, right? So how do we pair these two things together? And the core point here is that we're going to see is that the more structure, the more model that we can incorporate into these tools, then the less data that we'll actually need for the machine learning system to work. And so, if we can pour more science into our predictor, then we can pour less machine learning in and get just as good a prediction. So the overall idea, you might be like, okay, that sounds exactly what I want to do. But how the heck do I do this, right? What is the actual mathematical technique to go there, right? And this is what we've been developing a lot as the Scientific Machine Learning Organization and the Julia Lab, right? So you can read the original preprint and everything on the universal differential equations. The core idea is this, right? I think that this is whiteboard mode right here. Alrighty. And we got this in the camera? All right. Okay, I'll all right, cool. So let's actually start to look at this, right? So one of the things that people know about is, say, the Lock-Voltaire equations, right? And so let me kind of give you a little bit about where these equations come from. So you have a group of bunnies out there, right? So you say x prime is equal to the number of bunnies, right? And if you look out in nature, you just say, okay, if I have a bunch of bunnies, if I have some bunnies in a room, what tends to happen is you get more bunnies over time, right? They just tend to multiply. But we say that they multiply because every 2 bunnies can create a new bunny, right? And so if you have more bunnies, they have more bunnies that are created, right? The rate of growth of bunnies is actually proportional to the amount of bunnies, right? And so you say x prime is equal to, alpha times x, right? The growth rate in the number of bunnies that there are is proportional to the number of bunnies that there are times some growth rate factor, right? Don't know what the growth rate factor is, but this is where this model comes from, right? And then the other thing that happens, though, is if you have wolves, y prime is equal to minus delta y. If you put a whole bunch of wolves in a room, right, these are carnivores. They need to eat other animals in order to survive. And so what are they going to eat? Well, the wolves will eat other wolves, and the amount of wolves that are hungry is proportional to the number of wolves that there are. So so over time, you have a decrease in the number of wolves in your room, when it decreases faster for the more wolves there are, right? So these are very simple differential equations. You have the number of bunnies that you have grows exponentially. The number of wolves that you have decreases exponentially, right? Now, the thing that happens is to say, okay, well, what if I put bunnies and wolves in the same room, right? Well, see, here's the thing. What happens is the wolves, they actually prefer to eat the bunnies, right? So if there's a lot of bunnies, right? So if there's a lot of bunnies and there's very few wolves, what will happen is that the wolves will eat the bunnies, right? Or the wolves will eat the bunnies. But then you'll get more wolves over time. But what happens is if there's too many wolves and there's not very many bunnies, the wolves will start to starve to death because there won't be any wolves left, right? And so what happens is you have this oscillating behavior where the number of bunnies and wolves goes up and down, right? But even though we know that this is going to be happening in practice, the real question is, how do I modify my system, right? How do I modify my system so that way I can have some differential equation where I say there's some function of bunnies and wolves, and there's some function of bunnies and wolves that completes the model and tells me this is how the system grows, right? And now, while you can sit there, you can kind of derive a system or whatnot, what I'm going to show you is this idea of, well, it was very easy for me to give you this background. It's very easy for me to tell you these equations must be true, right, in isolation. But how do we find the more difficult equations, and can we do that automatically, right? So this is really the idea behind the technique of the universal differential equations. What we're going to do is we're going to use this scalable, learnable method, right? This method that's able to learn from data, this neural network object. And we're going to say, instead of trying to write down the whole set of equations, what we'll do is we'll write down every single equation that we know. And then for the equations that we don't know, what we're going to do is we're going to represent them by a neural network. And we're going to train the neural network to answer the question, what function goes here that completes the system to match the data? So this gives us a way so that way everything that we know about in our scientific domain, whether it's rabbits and wolves, or everything that we know about a climate model, everything that we know about chemistry, we're able to incorporate this all into the same way that we build models before, ordinary differential equations, partial differential equations, stochastic differential equations. But we use a neural network to be able to capture the functions that we don't know how to write down in the system, and then we use that to be able to generate the missing equations. Basically, the way that, when you go to Google and you type in autocomplete and then you tab, and it's able to figure out what the rest of the sentence is for you, or basically you're going to do that for the scientific modeling process, right? And the way that it looks like this. This might be a little bit complicated, but again, when I do this in a step-by-step way, it'll make much more sense. So I'm going to go straight to the step-by-step way. All right. So the step-by-step way is like this. First of all, so the test case that we're going to be looking at here is early on in the pandemic in the Wuhan region, right? Early on in the COVID-19 pandemic, let's say we had 21 days worth of data. So from 0 to 21 days, we want to be able to make a prediction about what the pandemic is going to look like after 21 days, right? So this is our challenge. We have the first 21 days of the COVID-19 pandemic, and we're trying to say whether a pandemic is going to take off or whether it's going to die out, right? And so the one thing that you might want to do is, as a baseline, what happens if we use just pure machine learning in this scenario, right? Just to see what happens. So what we're going to do is we're going to say U prime is equal to a neural network, right? So this is what we call the neural ODE. This is the version that is just saying, let me learn whatever function machine learning wants to say for the growth rate, and let me use this, right? What you see is you see these ideas, these issues of machine learning. You see it immediately pop up in this example, right? So we train this machine learning model from 0 to 21 days worth of data, and it says, hey, look, this is a perfect fit to our data. And then we ask it, well, what's going to happen for the pandemic in the future? And it says, you basically have no pandemic that's going to happen, right? And then a lot of people will throw out these like platitudes, and they'll say like, oh, this is because machine learning can't extrapolate, but all of that stuff is actually meaningless kind of bullshit, right? Like, so what really is happening here? Well, what's happening here is that machine learning does exactly what we told it to do, right? What we said is, U prime is equal to neural network. So we say, find any possible ODE that fits our data, and then continue solving that ODE past the time that we trained it on, right? And if you actually look at it, it found an ODE that fit our data, right? It found an ODE that fit our data, and it continued and extrapolated just fine. So the problem with machine learning going outside of data, extrapolating everything, is not actually some like high-level thing that you just say, oh, machine learning can't extrapolate. What's actually going on is that machine learning is learning from our data set, and it's finding a function that works perfectly fine. It's the wrong function, right? Because there are many functions that fit the data at the beginning here, right? There's an exponential function, there's a line, there's a quadratic function. There's many functions. If when you just have the little tiny tail here, there's many functions that work. And what machine learning did is it picked one randomly out of the hat, and then it just said, okay, I'm going to extrapolate with that one, right? So the issue is not necessarily that machine learning doesn't extrapolate. It's that if you don't have enough data, there are way too many functions that are able to fit your data. And if you want to make this thing work out, you need to make it so there are less functions that are able to fit your data. And as scientists, we do this naturally, right? How do we constrain the functions that we allow our models to be? Well, what we start to do is we start to impose assumptions that we know must be true. Right? So what are some things that must be true about these types of epidemic models, right? Well, one thing that should be true is that the number of people who are susceptible, plus infected, plus recovered from the disease, plus died, should all be equal to a constant, right? You don't have people just magically disappear. There's nothing about this model, and there's nothing about the machine learning that I put in there that actually says that this conservation law has to be true. So, in fact, it's actually violating conservation laws in its predictions. So this is one thing to know, like, okay, machine learning is going, it's able to pull from any possible function, but what if we can make it be possible functions that have, this conservation law be true? What's another thing that's going wrong here? Well, another thing that's going wrong here is that the number of people who are susceptible to disease, I didn't plot it here, the number of people who are susceptible to disease early on in the pandemic should always be decreasing, because if there was no one who had the disease before, more people were susceptible, but then as people get the disease, you have less people susceptible, right? So S prime better be negative. That's actually not true in the version that machine learning came up with, right? And so there's all these different pieces of information which we know should be true, but are not incorporated in just machine learning on its own. So if I wanted to force machine learning to go down the direction so that way it would only be able to learn in a way that matches my scientific predilections, how could I force it to be able to work in a way that matches what I know about the world, right? Well, it turns out that we do have a technique to be able to do this, right? So when you actually teach people how to do mathematical modeling, you're not necessarily just teaching someone how to build equations and you just go, oh, this is equations that people built before, right? When you teach someone how to do mathematical modeling, what you're actually teaching them is a two-step process, right? How do you write and solve differential equations? But also, how do you figure out what the phenomenological properties of those differential equations are to figure out if your equations make any sense at all? Right? And that second piece is actually the core here, right? Because when you write down a set of differential equations, right? When I wrote down this set of equations for the Lockwood-Terry equations, I said, oh, there's exponential growth in the number of bunnies. And you go, well, but the number of bunnies cannot go above 100 trillion, right? And so you say, okay, well, you have to modify the equations so that way there needs to be a decay term, so that way if it gets large enough, it'll level off, right? And so when you start to talk about this world of how you do mathematical modeling, you implicitly are not talking necessarily about the equations. You're talking about phenomenological guarantees that will come from writing down mathematical equations, right? So if we want to make our machine learning satisfy phenomenological guarantees that we know how to assume, well, then maybe the way that we can do this is by bringing our machine learning into the way that we do mathematical modeling, right? And so let me do this by example. So now, instead of trying to predict where the pandemic will be instead of making and predicting where the pandemic will be in 2 weeks by using that data and just a pure machine learning model, now what I'm going to do is say, hey, look, here's an SEIRD model, right? So in the pandemic, you probably heard way too many SIR models, right? This is this type of model. But the key thing behind this type of model, though, is not necessarily that it, well, here's the thing, right? So here's an SEIRD model. Susceptible individuals become exposed become infected become, they either recover or they do whatever D is, right? And so the key thing about this kind of model, though, is that there's one part that we don't know how to model well, which is exposure. How do you get exposed to COVID-19 was something that was really difficult because if you were in the lockdowns in China, you're experiencing a very different exposure function than if you're in the no lockdown situation of Sweden, for example, right? So I don't necessarily know how to write an equation that goes right here because it's way too, different country to country and all these things. But I do know that this type of model throws me in the right direction for machine learning. And you can see instantly from this that, training from 0 to 21 days worth of data, the machine learning is able to capture and get something that's almost correct for almost 2 weeks in the future, right? Again, same amount of data, but what I'm doing here is I'm saying instead of learning everything just from the data, what I'm saying is now take a structure equation where you say this is something like an epidemic model, but now learn a missing portion in the epidemic model, and boom, now it's able to start making these predictions, right? So one way you can justify what's going on here is I have put all of my knowledge of epidemics into the system, and I've added machine learning to that, and now machine learning has done better than machine learning on its own. There's also another more mathematical way to be able to look at this, though, right? So, for example, if you look at the equations here, well, first of all, S prime. This is this is a positive. So let's assume that the neural network output is always positive because you can always take its absolute value, right? So if the neural network output is always positive, then you have a negative, negative, negative. So F prime is actually always negative. So remember that assumption that I said, oh, machine learning doesn't impose this. Well, now for any possible neural network that is learned, it's always going to have that S prime is negative. It's monotonically decreasing. So boom, I put one of my assumptions naturally in. One of my assumptions that I knew needed to be true about the system is naturally imposed by putting it into the mathematical modeling form, right? Now, what's another thing? Conservation laws, right? Well, if you look at the differential equations, you have minus this term plus this term, minus this term plus this term, minus this term minus this, I actually have a mistake here. It should be plus that same term, minus this term plus this term, minus this term, So because of what we know about differential equations, S plus E plus I plus R plus D is actually equal to a constant. So we have conservation laws actually imposed in the system, right? Again, for any possible neural network, it always has to satisfy that S is monotonically decreasing, that you have conservation laws of S plus E plus I plus R plus D is always equal to a constant. What else do we have here? Well, you can actually prove that this model will always have, again, for any possible neural network, it's going to have at least one peak. The reason why it has one peak is because S is monotonically decreasing, E is first increasing, and then it's decreasing. So therefore, by the mean value theorem, there must be a point where E prime is leveled off. So therefore, there's at least one peak in this model for the number of people who are exposed, and there's also one peak in the model for the number of people who are infected. So what we're effectively, so you can say, oh, I imposed, my epidemic background, and I put that with machine learning, and that made this predict better, right? A bit of a wishy-washy way, but it's one way you can understand why this worked. Another way that you can understand that this worked is to say, machine learning is able to learn any possible function, and if you let it learn any possible function, it might learn the wrong function and try to extrapolate with that. But instead of saying you can learn any possible function, if I put it into the context of a scientific model, if I say, learn any possible function that goes here, well, every possible function that goes right there in the mathematical model makes the prediction still satisfy conservation laws because of the differential equation's results. It still requires that S prime is decreasing. It requires that there's a peak in the infections. It has all these properties naturally imposed because of the mathematical model structure around it. And so we now have found a way to force machine learning to only pull functions from the realizable set of functions that we know to be true about epidemics. And when it does that, it tends to give you better results on average. I think that, as a mathematician, that is a much more satisfying way for me to understand why this type of approach would work out. And then the last thing that you can do here is you can say, well, instead of just leaving it as a neural network, what I can do is I can have it spit out what the equations actually are. And so again, it's like truly auto-completing the model where you write down all the science that you know, you use the data, you use a sparse regression on the neural network, and then it spits out that this is the actual set of equations that I found, and it actually gives us two pieces here. One of the nice things about this is that when you actually decrease the generalization of the neural network, you actually increase the generalizability of the predictions. It tends to extrapolate better. There's some things that we're trying to prove along these lines. If anyone wants a nice PhD thesis, there's a nice way that we can probably do this proof by using properties of extrapolation of high-order polynomials versus low-order polynomials, but that proof isn't done yet. So it's a great project for anyone who's out there and looking for a reason to join the lab. Right? Second thing as well, though, is that it can actually make scientific predictions. So we allowed this neural network here to be a function of S, so this is susceptible individuals, I, the number of individuals who are infected, and the number of individuals who died, right? D, right? Now, one of the interesting things that comes out of the predictions of the equation right there is it basically just says that the number of people who have died is not, or the function for the number of people who are being exposed to COVID-19, it ends up, we allowed it to learn any possible function of S, I, and D, but the equation that it comes up with is not a function of D, which you can basically read it off as a phenomenological prediction that people who are dead are not spreading the disease, which, I mean, most people would probably think, okay, that makes sense. And, but this shows you that, you can learn these kind of hypotheses directly from this approach, right? So so this is the high-level approach, and there's a lot more to be said here. I think I'm going to be running into time limits. So what I'm going to do here is I'm going to switch from saying like, okay, there's a lot more examples I could show in terms of gravitational wave data and using this on race cars and yada yada, right? In fact, we actually worked with the Williams Formula One team with George Russell and y'all. But instead of doing all that, what I want to do now is I want to switch over to doing a semi-live demonstration of how this actually works in practice, right? So here what I want to do is I want to do the Rackauckas example, and I want to show you all the code behind it, right? So what we want to do here is we want to say, okay, here's the logical Volterra equations for predator-prey dynamics, right? And in this case, we're going to start with a known truth, right? So I'm going to tell you right now, these are the equations. I'm going to generate data from these equations. I'm going to assume I only know half of the equations, and I'm going to use the scientific machine learning method to recover what the other half of the equations are directly from the data, right? So this is the set of ODEs I want to start with. And what I'm going to do here is I'm going to pull in all of these really nice Julia packages, right? In a longer version of the talk, we can go through how this all works. In fact, if you want to learn how all this works in general, you search for the high-performance scientific modeling with Julia and SciML. This is a set a workshop set. You can also find this as the Julia Modeling Workshop, which has Pluto notebooks that goes through how to do all of the scientific modeling yourself, plus the machine learning aspects to be able to automatically recover the equations, right? But I'm just going to the final notebook here on the scientific machine learning part, right? So what we want to do then is say, okay, let's generate the training data. So how we generate the training data is we're going to write down the ODE inside of the Julia ordinary differential equation solver form, right? So we write down the ODE, and we're going to then do this for a time span from 0 to 5, and we're going to solve it, right? So this is a data set where, again, this is a data set of, we know exactly the ordinary differential equations that generates this data set because we're just putting the equations into the differential equation solver, solving the equations, and getting a time series out from the ODE solver, right? And so and then I'll show a plot of this. So here's the actual ODE solution, and then those red dots are the data points around it. You can see that there's a little bit of noise around it. I didn't want it to make a very simple version of this, so there's not very much noise. But here's our data, right? So we have the red dots, and we have and the red dots is all of our data, right? So what we want to do is we want to build out this kind of hybrid model, and we want to learn missing equations from an ordinary differential equation system, right? So how do we do this? Well, what we're going to do is we're going to first define a neural network. So we're going to use Lux here to define a neural network. This is just, if you go to the machine learning libraries, you see that you have to have an activation function. We chose the RBF. It can be pretty arbitrary as to why it's an RBF, et cetera, et cetera. That's the question for another day. But basically, we have a neural network, a small neural network. In fact, you can see that this is a pretty tiny neural network, the hidden layer sizes being 5. So in the grand scheme of, when I'm talking about, people are doing these, trillion-dollar, multi-GPU kind of neural networks, they're talking about hidden layers of, size 1 trillion or so. we have 3 hidden layers of size 5, right? So this will run on your laptop in a few seconds. Very different scale, but again, the reason why we're able to get away with this is because we're replacing a lot of the work of machine learning with expert knowledge, so that and augmenting it with just a little bit of machine learning. So you can see right here, it already shows you just a little bit of machine learning is what's being augmented with what we're doing, right? And so what we're going to do now is we're going to say, okay, let's write down our hybrid model, and let's actually look at this, right? So, what we're doing right here is we're saying, okay, there's a dynamical model that we have, right? There's some ODE. And the way that I define this ODE is you first get a prediction out from the neural network, right? So the neural network is predicting 2 values, right? And what we're going to do then is we're going to say that the derivative of x is equal to, the derivative of x is equal to some known parameter times x1, or times x. So this is basically saying, derivative of the first value, so x prime is equal to some known parameter times x, right? So x prime is equal to some known parameter times x plus whatever comes out of the neural network, right? Because again, this is any possible function. This is the output of any possible function. And then y prime is equal to minus a known parameter times y plus anything that comes out of the neural network, right? So here we've basically encoded this what I wrote on the board here, right? Where we say, this is an encoding of our idea of, I know this equation, add something to it. I know this equation, add something to it. Where the something is the output of the neural network, right? Now for an untrained neural network, it's, this something random is going to come out of here, right? But what we want to do is we want to do the training of the neural network. When we train the neural network, then this will actually be the correct function. And then what we'll be able to do is pull that out and actually figure out what function did it learn. So let's see how this ends up going. Right? So then what we do is we make this prediction function where you say, okay, you give me neural network parameters, so it's just basically a list of neural network parameters. It takes in neural network parameters, and it runs this differential equation. So it solves this differential equation with the neural network inside of there, and it gets some time series, right? But normally that time series is going to be wrong, right? Until the neural network has the right parameters, that time series is going to give you garbage, right? So what you have to do is you have to train this model. And how do you train this model? You build a loss function. This loss function is say, okay, take in neural network parameters, theta, run the prediction in order to get a time series for what x is like. And the difference between the time series that you're spitting out from that model to the data set, that should be going to 0, right? And we want to minimize this cost function. So we want to make the time series that's being predicted by what's coming out of that model be as close to the data that we have in our data set. That's all that's essentially saying there, right? So it's basically saying, there's some random f, there's some random g, that we've added some random functions now to our differential equation, and just keep on changing those functions around until you find the ones where solving the differential equation with those random functions augmented to it ends up giving you the solution that matches our data set. And then there's all these little details that is on top of that, yada yada, for how you actually do the process. Again, a longer version of this workshop walks through every single line of code, but I'm trying to stick within the 5 minutes left time frame here. But when you do the training here, what you see is that, again, at the start, the predictions are not anywhere close, right? At the start, the predictions are not anywhere close. In fact, they're 1 times 10 to the 7th off, right? So adding a random neural network to your equations, especially with ordinary differential equations, you end up getting a solution that's just way, way, way off, right? But what it starts to do is starts to find better and better neural network parameters, be able to hone in on how exactly this behavior is, until by the end of it, it's able to give you something that's a very good approximation to your system, right? So again, the first loss, so the first time series difference is all the way up in 1 times 10 to the 7th. But by the end of this training process, it gets down to something where the difference between the time series it's spitting out and the time series and the original time series of the data is the summation over the whole thing is 1 times 10 to the minus 2 or 1 times 10 to the minus 3. Now, again, I'm going fast over this portion because I'm just going to say how the training process works. This is the graduate course, 18337, the math course at MIT. We spend months and months and months going exactly how the math of this works. But if you use the software, you basically just say, build an optimization problem, click solve, and then will spit you out effectively the neural network parameters that makes the training process solve, right? So we'll skip over that big training part just to say that's where all the actual math is, right? But when you do that, let's actually see what we get, right? What you get is here's the prediction then for the learned once we have the learned neural network parameters, this is what it's predicting the output of the ODE would be for the prey and for the output for the predator, right? And you can see that it's effectively found what the missing F function is and what the missing G function is, right? Now, but it's only representing it as a neural network. So as a neural network, what we can do, though, is we can put values in and it spits values out. What those values are is effectively the missing parts of our differential equation. It's basically what is the amount that our x prime and our y prime values were incorrect, right? And now, but it's not really that useful. So what we want to do next is you want to say, now that you've actually found a computable element that tells me the value off by which my original model was, can I convert that neural network representation to a human readable representation for what I was missing in the model, right? And so what I'm going to do, this is that next part then, which is a symbolic regression aspect. So what we do then is we say, okay, what we actually have here is we have a function of x and y that we can spit in. So what I'm going to do now is I'm going to take a bunch of values of x and y. So I'm going to take a bunch of, values of x and y. I'm going to put them into there, and I'm going to build a data set that's going to be x and y goes in, and f of xy comes out. I'm going to have a data set of inputs to outputs. And I'm going to now pull this out of the system and say, there's no more differential equation. Now let me learn just in isolation this mapping from xy to f of xy. And so again, the details, all the details are covered in the code. And you have to be, in order to run this method, you need to give it some basis in order to be able to learn from. And we're going to say, well, from the set of all polynomials up to order 4, find the simplest version of the polynomials that is able to then satisfy what is the function that represents the neural network training, right? So you can see this is the polynomial basis that we're then pulling from. Again, going quite fast over here because each one of these could be a 2-hour lecture for how each of these steps works. But then we're basically going to run this, and then I want to show you two things. Right? So the main element that I've been trying to tell you here is that scientific machine learning, this idea of putting expert knowledge in, is able to improve on what doing machine learning on its own is able to do, right? So one question that you should have with this example is, if I tried to just make the machine learning learn all of the equations itself, how well does it do, right? And we actually have this answer inside of the notebook. It says right here, so if you were to give machine learning the ability to try to learn all of the equations, here's the equations that it comes up with. It finds that the equations are best linear in U1, best linear in U2, best linear in U2, right? If you go up to your original equations, you can see if U1 is x and U2 is y, it didn't even get close because it needs to have a quadratic term here, it needs to have a quadratic term here. In fact, for this type of mathematical model, you cannot have this kind of behavior, this kind of oscillation, which is not just a circle, without having a quadratic term. Like, it's actually impossible with a linear ODE model. And so you can actually see from this right here that if you just did this process without the prior scientific knowledge, if you did the model without this prior scientific knowledge, then it gives you out this prediction, and therefore it didn't work, right? Now, is this to say the machine learning can't work? No, the problem is that we had a very small data set, and you need a huge data set for machine learning techniques to work, right? So this shows you that if you just learn the equations for me, this doesn't work. But what if we had this process, right? So when we train the neural network to just learn the missing equations, if we now perform the symbolic regression just to learn what the missing equations are from this data, what does it come up with? And you can see from this, you get that you're missing this term, quadratic term, and you're missing this term, quadratic term, which is exactly what we expected, right? Because remember, what we did in this example is we presupposed that you knew this term, and so the missing terms were constant times xy, and the other missing term was constant times xy, and that's exactly what the machine learning was able to come up with, right? It was able to show you that, say, hey, look, that thing that I added to your equations that completed your model is a constant p1 times xy and a constant times xy, and boom, it was able to basically find exactly the missing terms of the model. And then what we're able to do is we're able to then say, okay, now that we know the missing equations, we can throw the missing equations back into the system. And the final thing here is that, again, we only train on this tiny little data piece right here, But then we predict going forwards. The blue line is our prediction. The green dashed line is actually the data. And you can say it's very difficult to look at the difference between the two, and it's because it's pretty much a pretty exact prediction. And the reason why it's almost an exact prediction is because it's actually learned exactly the correct equations, right? There's no neural network here in the end. And once it found what the correct equations were, it's able to get a very good prediction because it's not trying to estimate these equations anymore. It's making the true extrapolation with the actual equations that it found. And so this shows you the scientific machine learning process in full. Again, there's so much more that can be said here, but this shows you that, this is one way to start to look at this space of machine learning and say, hey, look, people are doing a lot where we're learning from data. Where can I, as a scientist, be able to work in this space? Well, what I can do is I can bring everything that I know. I can bring, all the equations of a climate model. I can bring all the equations that I know of chemistry, and I can presuppose these into my model because I know it's not covered by my data. But I can use these tools as a way to be able to learn things, to learn what error was I missing in my model. How are we supposed to account for plankton if there's some event that say puts more oil into the ocean? How do I account for that effect in my plankton model, right? We can use the fact that these tools exist to make us better at building models quicker that are more accurate. And so that is the first thing I wanted to capture. Where do humans go in the age of AI and machine learning? This is one way that we can be incorporating it. The next way we can be incorporating it, though, is with agentic AI. And I think that then will come after the break because we're supposed to have a break right now. Yeah, but I will take questions. Yep. All right. I can run.
You have to share.
Oh, I can use the other mic. Yeah. I can be constrained.
Thank you, Chris. It was a great talk. Look, I'm going to ask you a question as a physicist. Okay. So I was learning. My mind was going. Okay. Imagine you had, going back to the 19th centuries, imagine that you had Faraday experiments.
Mm-hmm.
Could your equipment find Maxwell equations? Or if you had, say, the data from the speed of light and for instance, the Lorentz equations, which is just the same as the Einstein special relativity equations. The difference is just the way space-time is understood. Would you change that axiom at a deeper level? And finally, the third question, you see it's mostly the same question, just three different aspects. If you had if you look at the cosmological data, could you guess if it was general relativity or some other approach to general relativity, like myriads of physicists have tried, and can you distinguish if one is better than the other by looking at all the different types of differential equations and tensor equations that can happen? Thank you.
Yeah, very, very good question. This actually comes to some of the things that we've been working on with some collaborators. Again, this is not quite in the climate space, but one of the things you can go to is if you go to docs.sciml.ai, you go to our showcase, right? In the showcase, you'll find automated model discovery. You'll find discovering relativistic corrections of black hole dynamics. This is actually an example where we say, okay, and this is done by one of our collaborators in a published paper, so you can read the paper or whatnot. But we turn their paper into a documentation example at this point, where what you do is you say, okay, assume that you only knew Newtonian physics, right? Assume that you only knew Newtonian physics. So you write down the two-body problem for a Newtonian system. The solution would be an ellipse, right? Now, if it's a black hole system, black holes are relatively big, right? But now if you have two black holes going around each other, then you must have relativistic corrections, right? So can we automatically learn what these relativistic corrections are from data using gravitational wave data from LIGO, right? And so this is a complete example of doing that. It's simplified how the data works so that we don't have to download data each time, yada yada. But you can basically see that it starts from a solution that is an ellipsoid, and it learns what the relativistic correction is. The relativistic correction is a small change to the equation. equations, right? But once you learn that small change to the equations and you extrapolate it out, well, then when you get a different orbit, and then orbit gives you the Lysygy pattern that you expect, right? There's the same thing as the Lysygy pattern of Mercury around the sun, right? And so this is exactly that kind of thing where it's just learning what is the small equation correction, and once you extrapolate out then the differential equation, it says there's actually, once you learn the small correction, you actually get a completely different phenomenological prediction from what the orbit would be. It should be the Lysygy pattern, which you can then say, okay, now let me see if I go find that pattern, and then that would be this, right? And this is actually how this is actually the process for how general relativity was first proven, right? The perihelion of Mercury. So this shows you that at least something similar to it can be done with the scientific machine learning pieces, where again, a human is kind of saying, if I start with Newtonian physics, I cannot make things match the data. What is the minimal change to the equations that I can do? And then what is the long-term effect of having that minimal change to the equations, right? So I recommend you go through this example that goes through the step-by-step about how this is done. Now, when you're talking about the cosmological models, there is actually a group that's bringing this into cosmology. I think that it's called symbolts.jl. So symbolts is a symbolic numeric cosmological model, which is fully created using the JuliaEO26 ecosystem. It has a full model of inflation and cosmology, et cetera, and it's using this with the whole modeling toolkit ecosystem in order to then be able to use the scientific machine learning to be able to figure out what are the standard assumptions of cosmology which are incorrect that need to be changed in order to make better predictions of the system. So yeah, if you're into cosmology, I'd say go check out Symbolts, because people are now starting to use this in the SciML space. So I love the question because I've been helping this guy, all the last few months, and so it's really cool that I get to bring this up. It's the paper is just super cool. So.
All right, very different question, I guess. When you're ready.
Yeah, I'm ready for it. I just wanted to kind of show something on the screen while while you're talking, just like kind of like back matter, doing an advertisement for somebody.
I'll wait.
Well,
okay.
As American, we do have a lot of advertisements as you walk around everywhere, so we're used to this.
All right. So my question is about the beginning of your talk. So another thing that humanity is doing right now, I should say Silicon Valley is doing right now to crash the planet is, in addition to building data centers to train AI to make us comfortable, they also, there's the cryptocurrency business that changes the rules in a way and changes the relativity to money. And that same sort of group of people also considers that the timeline is finite, that in 20 years we're post-human, so none of this matters anymore. So I was wondering if you take this extrapolation that you had at the beginning in terms of cost, if you were to express it, not in US dollars, but in Bitcoin, how that looks like, and once you put a finite time horizon to it, how does it affect your thinking?
So yeah, that's a really good question. I mean, let's go back to how the numbers are evolving to just kind of get a feel for it, right? Basically what seems to happen is that there's a generation about every 2 to 3 years, and at each generation we get a small increase in AI accuracy for about the 10x in the cost, right? You go from the 10 billion range, and then there's the 100 billion range, which is mentioned, 100 million range, which is mentioned right here, right? And then what came after that was the 1 billion range and the 10 billion range. We're now entering into the next generation, which would be the 100 billion range for the training, right? Again, GPT-4 to GPT-5, most users didn't even notice the difference, right? GPT-5 to GPT-6 is going to be $100 billion to be able to do. Expected to have a very similar difference. Do we really believe that the $1 trillion range is going to be the one that kicks us over the line, and we don't have any work? Again, like if you look at how this is 10xing each time, I just can't see that. Maybe generation 10 down the line is the one that does that, but 10 generations down the line is talking about quadrillions of dollars. I don't see an economic possibility where it's able to literally do everything, right? So again, the second part of this talk will go into these systems are pretty good. How do we start to use them? But I really don't think that they're going to be doing, I don't think that they're going to be getting to even the PhD level anytime soon. I would put that the level that they're at right now, the $10 billion to $100 billion range has gotten us something where it's about as good as a competent sophomore, second-year college student, right? And so, okay, the $1 trillion range is going to get us, a competent, fourth year undergrad. I think we can start to say, okay, the 10 trillion version where it gets you like a first year PhD student or so, the math doesn't work out that it's going to completely replace you. It's going to replace a lot of people, right? Because the number of people who can code and know science as well as, a third year PhD student is a very small percentage of the population. So a large portion of the population should be extremely kind of worried, right? But I do think that there's still a place for experts just because how this exponential growth in cost, when you take into account the exponential cost growth along with how the rest of AI is growing, I just can't see it actually doing the next doubling because, yeah, it's been growing. It's been going exponentially for 6 decades, but exponential growth is really hard to do for a very long time. And so we're hitting the fundamental limits here.
Okay, congratulations for your presentation. I believe that this is the way. I am a guy that understands a lot of Voltaire equations. They are very good. They are a very good example to explain.
They're my favorite ODEs. Yeah.
Yeah, they are really good because they are understood by most people, and if Plato and Aristotle they would be here. Plato would be for the equations that you are using, and Aristotle they would be just for machine learning. And because you used to say that what exists for Aristotle, what exists is what you see, and for Plato, what exists is what you understand. And so to understand, you need the equations. So I think we will talk afterwards more about this because the Lotka-Voltaire equations, they are a good example. But in fact, what we want for the prey and predator model is a more complex system of equations that are many terms like these ones with plus and minus that you have shown to cancel. But we need to have more variables. And so, is there many people working using this philosophy, or not so many? Or?
Yeah, I mean, in 2019 when we created the SciMo organization, there really wasn't a field of this at all. But now it actually is a field that has a name, right? It's the field of scientific machine learning. It still doesn't have a Wikipedia article really, but it has something that has been come along, and you can see that the scientific machine learning organization in Julia, this is the organization that I've been driving with open source software. This has been the community that we've been building. We now have about, if you look at the documentation, there's about 300,000 downloads from unique IPs every single month. So this gives you it's in the 300,000 scientists or something that are kind of using some element of these tools, downloading it every month. And so we estimate the number is about 500,000 at this point, right? So it's still a small group in comparison to a lot of things in the world, but there is a group that's saying, okay, maybe this is the approach to science that we should be doing. And there's a pretty wide community, and so you can join our chat rooms. I think that the Julia chat rooms does have 15,000 people who will respond to messages. So there's quite the activity going on, but still, even in these numbers, right? There's tens of millions of scientists in the world. 500,000 are kind of going on this route. I believe that number is going to exponentially grow to become every scientist needs to take into account these ideas. But but right now we're still kind of at the early stages. So yeah, if you look for everything that's going on in SciML, scientific machine learning, this is the language that we've been putting it out and the conferences that we've been putting on. In fact, hopefully we'll have a conference here in Tessera on SciML in about March or April as well. So yeah, it's grown from something that's just a few people at MIT to being a kind of a movement and a change in how we're thinking about science. Yeah, and kind of go with your metaphor here. It actually made me think of a different metaphor, right? You said Plato and Aristotle, right? If you want to think about it in terms of Sith Lords, right? It's kind of like Darth Sidious is like he's like was trying to be like, the way to do all science is that we have to control everything. We have to control all the mathematical modeling, right? Darth Vader comes in to just say, I'm going to use my passion to just learn from everything, right? But Darth Vader was only able to overthrow Sidious when he actually pulled in Sidious's methods and then put him down, right? And so he so the Sith Lord is only able to take over, be able to overcome the other Sith Lord when he incorporated their other methods. So maybe we should take that into heart as well if we want to become proper Siths.
Okay, thank you very much.
Yeah, just another quick one. Something that I'm not very familiar with, but have you heard of this Denario project? I think that's coming out of the Simons Foundation.
Yeah.
And somebody pointed me to this paper. The theme of it is that they are now using AI agents to essentially write papers from scratch. Is that something you want to comment on, or have?
Let's wait for the second part, because the second part will be on the large language model usage.
Thanks, Chris, for the wonderful presentation. I just wanted to ask, it's just the validation, differential equations as they are, you took the case of Lotka-Volterra, these are the very simplified versions at the SIR set, it's not the actual depiction. And once you use symbolic regression, again completing the loop and generating, can this be further used? Lotka-Volterra can be used in many, like in economics also, and in fire studies also. So can we use, closing this thing, can we create data which can be actually used to again retrain the machine, to retrain the machine, and make the things closer to the actual scenario?
Yeah, so I mean, I'll say that, the example that I showed here is kind of like the teaching example of like, oh, here's an example I can show in 5 to 10 minutes and show you every bit of the code. But a lot of the true examples of this being done in the literature is now, doing this with, real world data on much larger equations. I think that one that I like to really point to is this one on absorption modeling. So this is one that's on modeling chemical plants. And in the chemical plant model, effectively what's done here, I guess, let me try to see if there's an open access version. Yeah, you can always find the archive version, right? And what's going on here is it's presupposing not that it knows anything about chemical reactions, but it's composing a diffusion advection system, right? So it's like embedding a neural network inside of a partial differential equation, where it says like, okay, I know that this molecule is diffusing and advecting, the other one is actually constrained to the reactor, and it's using, it's a much more difficult system, and doing this with real world data, yada yada, and it's showing that similarly that in this kind of scenario in chemical engineering, it works out. And again, there's now thousands of citations on the paper, so there's a lot of different examples of this in different scenarios. What I would point to is if you want to look at more of these examples, there is a talk that I gave, which is, let me see if I could find it easily, Accurate and Efficient Scientific Machine Learning. If you look at this talk, Accurate and Efficient Scientific Machine Learning through Differentiable Simulation, this talk actually goes slide by slide along, showing, for example, this in aerospace engineering, this in building engineering and civil engineering. So there's a lot of different validation points there. For this version of the talk, I cut out most of the validations just to kind of go straight towards one example within a 1 hour period. But these other examples are, like, instead of trying to show code, they're more trying to show the more complexity, right? So different versions of this talk give you different aspects. I recommend you check out this talk because this covers what you were looking for there.
I have one question.
I have one answer.
Okay. What SciML model would you recommend for fitting differential equation to long-term environmental data sets?
Yeah. So what I would do is I would just find, in whatever field you're in, someone has been creating differential equations, right? Someone has been modeling, so long-term environmental data sets, right? I mean, a lot of people in this room build long-term climate models and these predictive models, right? So what I would do is I would just go to, Milan over there. He has speedyweather.jl, right? And, it's like, okay, if the type of model that you need is some kind of weather model, or, okay, if you have a model of the current environment, go find the person who is actually building the model in that space. They're the expert in this, and start from their model and incorporate machine learning into the modeling that they've been doing, right? So as someone who's not necessarily in the environmental modeling space, I can't necessarily tell you who's the person to go to there, but I can guarantee you there's someone who's building mathematical models of it, and that's the person to start from. And that's the key thing about this technique, right? It's about starting from the scientific knowledge that we have. Go find the person doing the differential equations in your space, right? I know this. I know the things from my spaces, the biochemical models and such. But when you go into like certain climate models and such, go talk to the people who build out Klima and these kind of models, and then really start to ask the question of, okay, if you have a complete predictive climate model, how do I add machine learning to this, and how do I do my part to add this? The actual doing scientific machine learning in those contexts has a difficult computational and mathematical problem to actually train the neural networks and such. But if you can get beyond that part, then that's the groups to work with, right? The ones who have the most predictive models right now in the space.
Thank you for a good talk. It's really interesting to hear about this combination of science and machine learning. But I also sometimes hear about it in other contexts where it doesn't refer to like the JuliaSML community. So it seems like in Python and other places there are been taking other approaches to combining science and machine learning. What are your thoughts about some of these competing approaches and views, and how do they fit in, and what's the maturity of them?
Yeah, so that ends up being kind of a different talk, and I can show a few things there. I think that this talk has one of it. One of the things that you can see, for example, is that you do have some approaches in JAX where you say instead of trying to come up with different derivative approximations and such, maybe you can just do differentiation of the simulations. I have a talk which shows that actually that approach doesn't converge to the right answer, and provably even in very simple scenarios. So here's an example. Here's an example with JAX just on a linear ODE. You tell it to do automatic differentiation of the linear ODE, and it gives about a 60% error. And as you send the amount of, as you send the tolerance of the solver to 0, it actually does not change the error in the gradient at all. And again, there's a talk that I give that's this. You can find it on YouTube. It's the numerical analysis of differential simulation. We also have this inside of one of the review papers. It describes exactly why some of these other approaches might not be convergent to the right answer. In fact, you can actually prove that this version, why it's not convergent to the right answer, right? So there's a lot of little details in the mathematics that needs to be taken into account, where if you try to just do this with general machine learning techniques, a lot of the difficulties in terms of numerical analysis, handling stiff equations and things like that, ends up making it so that way real world equations have non-convergent derivatives and non-convergent estimates. And so what we've been doing a lot in the JuliaSML space is making sure that we can have incorporate the ideas of numerical analysis. So the same way where you just say, hey, look, one ODE solver doesn't work for all things. What are the different ways to calculate gradients and everything such that we can provably make this stuff convergent? And that, that's where the deeper math and science comes in, which I kind of cut out completely out of this talk, but you can go find the other papers and such that go into that. So when you see a lot of the software that we use and stuff, there is a lot of details as to why we do these techniques, which again is, if you come by MIT, go to the 18337 course, we'll go through all the proofs. So that's one piece, right? So it's why we do a lot of adjoint methods instead of just differentiable simulation, because automatic differentiation is not convergent. There's another thing that you will see sometimes, which is physics-informed neural networks. Which I'm trying to find where I have a piece that kind of shows what I wanted to show there. But the thing about physics-informed neural networks is, so we're using the idea of, if we have prior scientific knowledge, we should use all the prior scientific knowledge that we have, and then only augment what we need to with machine learning, right? The issue with going it's right here, right? The issue with going the physics-informed machine learning, physics-informed neural networks approach is it's saying that, okay, what we should do instead of trying to solve the equations with solvers that we have is we should also use the neural network to represent, to do the solving process, right? So what we are doing here is we're having the neural network represent the derivative. The fundamental difference that you see in a lot of places with the neural operators in the physics-informed neural networks is they're using the neural network to represent the integral, right? I think that there's a few reasons as to why you, based as a mathematician, just go, that's got to be the wrong approach, right? One reason is because derivatives are always a simpler representation than integrals, right? In fact, for example, it's very easy to write down derivatives that don't have an integral representation, right? The integral of e to the minus x squared, the integral of a normal function does not have a function representation in elementary functions, right? And so that if you're trying to make the machine learning problem as simple as possible, you want to represent the derivative, and so that's one thing to do. The other thing is to say, if we're trying to use as much scientific knowledge as we have, one of the pieces of knowledge that we have as well is numerical analysis, right? So many people in this room have studied how do you do accurate, what is the most optimal way to calculate integrals and all these things? How do you solve differential equations, right? We can actually prove, for example, that Gaussian collocation has the fastest, is the fastest way to be able to integrate polynomials because you get higher order, yada, yada. And so if our approach has been to incorporate machine learning into the tools of numerical analysis that we know are optimal, rather than trying to have the machine learning also have to learn all the numerical tools. And what you end up getting from this difference is, for example, here's looking at the difference between, so DeepXDE, right, which is the physics-informed neural network library, and PyTorch. In order to be able to learn the parameters of the Lorentz equation, it took 362 seconds in order to do the training process. This is actually just a screenshot pulled from their tutorial. When you do this with diffq flux in this differentiable programming approach, it takes 0.03 seconds, right? We're talking about 10,000 times difference. And the reason is because if you try to say, I'm going to make the entire problem be a machine learning problem, they use really large neural networks to be able to do things that we know how to do with very simple, Rackauckas methods. So another thing that's kind of implicit in our approach, that's the kind of like the JuliaSciML approach, is to say, let's do scientific modeling with all the tools that we have and a little bit of machine learning, right? And again, as I showed in this example here, when I say a little bit of machine learning, I really do mean, we have a very, very tiny neural network here, right? We have a neural network that has 3 hidden layers, right? 3 hidden layers of size 5 each. This is the tiniest neural network you've ever seen. So we're doing a lot of scientific approach with small neural networks. The other groups are trying to look at this as a problem of really big neural networks on GPUs and, a little bit of scientific knowledge. And you can see the difference. You can see the difference immediately when you actually look at the numbers that, it takes 10,000 times longer, it takes GPUs, and it has less extrapolation properties. And so, again, that's a different talk that I give, but there are some good things about the neural operators. In fact, if you're going to be working on very high-dimensional partial differential equations, their kinds of approaches will do better because the approaches I'm talking about here require that you already know how to write a solver for it, right? So, if you don't know how to write a solver for equations, so if you have a Volterra integral partial differential equation or something, right, then using an approach that is fully machine learning might be a better fit. If you have a 100-dimensional partial differential equation, that might be a better fit. But if you already know how to do semi-discretizations of PDEs for, climate models and such, why not use all that information? You'll save 10,000 times in your compute. So I think what ends up happening is it ends up segmenting where we end up working on very different looking problems for that reason. Where the problems that we look at is a lot in ODEs, DAEs, and partial differential equations that we know how to do discretizations with. And the more of the focus then of the other SciML groups tends to be things like Schrodinger equations and hundreds of particles where there's no representation in terms of differential equations. So great question. But yeah, I could show you the other talks that goes into that in copious amounts of detail, but that's really where the difference is, that we represent derivatives and use solvers, they represent integrals and use the machine learning to do the solve, and there's the pros and cons of that.
For someone new to Julia and SciML, what is the best starting workflow to go from a mathematical model to a working simulation?
That is a great question. So I'd say the best starting workflow is to find the Julia modeling workshop, right? Because the Julia modeling workshop starts from how do you use Julia, getting started with Julia, how do you install Julia, how do you build arrays and matrices, how do you write down a model for a differential equation solver, and only at the very end, after teaching you everything, it then says, here's how you use scientific machine learning with it. So it's really a starting from zero to hero kind of approach. I would say that these workshop notes, these are ones that we're pretty happy with. They're kind of new as well. They're just created 4 months ago. Other thing that you can do is you just go to docs.sciml.ai. There's a getting started here, which goes all the way from the start for new user tutorials. And you can see build and run your first simulation. This shows you from the very beginning, how do you start with Julia and get started with this. And it goes all the way down to discovering general relativity, right? And all within one documentation. So again, you can start all the way from the start and go all the way down, and we have the resources. Now, if you want more resources, what I would say is there's two things to do, right? You can always go to the Julia discourse, so discourse.julialang.org. This is where you can always ask for help in a public forum. So if you're running into any issues, I get hundreds of DMs from scientists every single week about, here's my ODE, here's my data, what's going on, how to improve this, right? If you want to send an email, feel free to do. If it needs to be confidential, you can always keep the models confidential. And so this is how you can do it a bit more publicly. If you want to do it slightly less publicly, I'd say go to julialang.org, hit on community, hit right with these right here. Zulip or Slack are really great chat channels. This will get you into the chat channel. Again, there's about 15,000 people in these chat channels that can help you with, oh, I tried to write this in my ODE solver. I got this error. What do I do? I think a lot of the people in this room probably all met each other through the Slack channels, right? And so, if you want to get started, I'd say, don't just look at this as, hey, look, here's the documentation. But there's a huge active community. Look at the documentation, but also join the community. Feel free to ask questions. We're accessible. We don't bite. In fact, I'm here on Terceira Island. If you want me to pull out my laptop, you can always find me at the Texan after karaoke, and boom, bring a laptop, and we'll between songs we can get your model working. So